Welcome to the third video in the work and energy topic. In this video we will be looking at how to calculate the work done by a variable force. So in the previous video we saw how to calculate the work done on an object if that object was acted on by a constant force, and we looked at the example of gravity. So if we start here by looking at a graph of a constant force acting on an object as a function of the displacement of the object, we can see the force doesn't change, but as it acts, the displacement increases. We know that because the force is constant, we can calculate the work done on the object by the dot product of the force and the displacement. Or if we look at the one-dimensional example, we know that that's the force times the displacement. So in one dimension, that's the area under the graph. So what happens then when we start looking at a variable force? We know that our equation, f dot s, is only valid for the constant force. So what we do then in this case is we start by looking at a very small displacement over which we can say that the force acting, or the force that acted to produce this displacement, is constant. So hopefully this problem, or the shape of this problem, is starting to look familiar. So since we can now approximate the force for this tiny displacement as a constant, we can use our equation. And we can say that the work is equal to the force times this little displacement, delta S. So that gives us the work done is equal to a little piece of the area under the graph. So then our total work is just the sum of each of these little works for each of these little displacements. And if we make those changes in displacement really quite small, we can write that the work is equal to the integral of our force as a function of the displacement. That is, it's equal to the total area under the graph. So as an example, we'll have a look at the spring force. So you've already worked with springs and the spring force, so just as a short recap. So the spring force is a restoring force. It's given by Hooke's law, negative Ks, where S is the displacement of the spring from its equilibrium state, and the force will always act to restore the spring to its equilibrium state. That is, the force, or the spring force, changes with its displacement from equilibrium. So in the case of our spring force, we can say that our spring force is constant for a very small displacement. And we can say that because we can choose that displacement to be small enough that our statement is true. Since we can do that, we can use our integral from the previous page and say that our work done by our spring on the mass m is equal to the integral of the force. The first thing we then need to do is to substitute in our formula for the force, which in this case is minus ks, and we can take the k outside of the integral since k is constant. Once we have our formula, then we just need to solve it, and we can solve it using the integral tables, which tell us that our spring force is equal to negative half k times the difference of the square between the initial and final displacement. And this method is how we deal with all variable forces. So I'll leave you with a final small question. In this case, based on the initial and final positions of the mass m, how would you know if positive or negative work has been done on the mass?